All right. Okay. Again, just stop me if you have any questions. Uh, I think Zoom will tell me whether you have put in another chat or not, but I think that ask me anything because it's on slideshow mode. I won't be able to see it. So just put it in chat if you have any things that you want to tell me. Okay. Let me get some water and then we'll start off. So decision trees are probably the easiest form to understand of machine learning because it's the most close to what most people think about when they make decisions, okay? What we say is that how people make decisions is usually not like a linear model, okay? Because linear models take every single feature, attaches a weight, maybe zero, okay, but attaches a weight to it and makes a linear combination, a dot product, accumulates that and says, okay, well, did you get a positive number or a negative number? If you got a positive, then the answer is yes. If you got a negative, it's no, right? So people don't do that. We basically have a limited amount of attention. So we usually think about, taking a important feature and making a decision based on that. Okay. So that's what we're going to do. Okay. So when we actually program, we're doing a decision tree too, right? Because basically we have a number of conditional statements and we would like to reach a programming block that we want to do. Okay. But we are conditioning it on some features of how the code or the state of the algorithm looks, right? So here we have an outer test one and then two inner tests, test two and test three, that tell us which of the 4 blocks of code that we are going to run. Okay, so we can think of this as a decision tree where we've picked the most important state of the algorithm and put that into test one. And depending on the outcome of that, deciding whether to test for another part of the state test two or a different part of the state test three, and decide whether we want to do one of the 4 blocks. Okay, so when we think about the parts of a tree, basically, you guys love trees. You're computer scientists or are studying computer science right now. So you already know we have internal nodes. They're going to be decision nodes. They're going to be tests. Okay, and in decision trees, for the most part, a node is testing exactly one component. Okay, so you pick a particular feature of X, say X1. Okay, and say, okay, I'm looking at you. What value do you have? If you are higher than a certain number, go this way. If you're lower than that, go that way. Okay, so this is a binary branch, okay, most of the time, okay, except when you have an attribute value that's enumerated, right? Like in the case of credit history, it has 3 different values. Then you can say, for each particular value, I'm going to make a subproblem, okay? And what I'm going to do is decide at some point when I get down to the base of the tree, okay, that leaf is going to tell me what to do, okay? It's going to tell me what y value I'm going to pick or a formula for how to decide the y value if it's a regression problem, okay? So that's the idea. Okay, so we can take a look at any one of the problems. We can pick another one called play tennis, like enjoy sport, like we saw earlier. Okay, it's another data set with the same type of information. And basically, we can decide, maybe we are going to look at the outlook because in Singapore, for example, if it's sunny, it's probably not a great idea to go play if it's really hot. But definitely when it's rainy, it's not nice. So the preference is to do something like overcast, right? So we're going to look at that and say, I'm going to recurse on these 3 things. So I'm going to take all the sunny cases and treat them as a subproblem, okay? So I'm just going to look at all the sunny days on this part, okay? And I will decide, based on that part of the data set, what else that I want to do, okay? And the same with the rainy ones, right? So all the rainy instances I just gather to one side, and I'm going to study it separately, okay? So I decide for sunny, well, it's Singapore. If it's humid, just forget it. I'm not going to play. All right. So if it's humid, sorry, I'm not going to play. If it's less than humid and it's not too sunny, later in the afternoon, maybe I'll go and play tennis. If it's overcast, definitely I want to play. If it's raining and it's windy, forget it. especially if it's strong. But if it's weak, it's sort of nice, right? So I'll say yes. Okay. So from this discussion, you can get two things out of it. We have to pick an attribute, okay, one of the features that we have in our x vector. And then what we need to do is to do what? We have to decide um, to recurse, okay? Basically, to take the elements and structure them as a separate subproblem. You can see why the slides are not done. They're not beautified properly. Okay, so we end up with something that we might have as a test case. So this is supposed to be a test case. Sorry about that. So you have a day. Its outlook is sunny. It's hot. So it's humid. Okay, but we decided based on what we said, right, that we're going to go this direction, right? So this is going to be yes, right? Because the outlook was sunny. So we went this branch on the left, and then we saw the humidity was less than 80%. So basically we ended up with a decision path that looks a little bit like that, okay? So we went down those two nodes. Okay, so when we think about the types of decision boundaries it makes, it's just like what you saw in Ada Boost just now when we were going through that question. It's basically making axis parallel decisions, okay? So it's very different from a perceptron because it's, perceptron is basically taking a linear combination of all of the different attributes. Here we're limited to just one, right? Just one attribute. So here we said we're going to take the idea of outlook. Outlook is an enumerated value with three things, okay? So I have to basically cut on these attributes into three different subproblems. And for one of the subproblems, I'm actually done. When it's overcast in my data set, as you saw, let's see, around here on slide 8, all of the overcast examples were positive, right? So you can see here, those were both positive. So I don't need to do anything else. Those guys are finished, okay? All right. So if I look at rain, I had to decide, right? So I said, if it's raining, I'm going to look at another decision. I chose wind, right, over here. And so I could decide whether it's strong or weak. And I'm going to split that up. For sunny, I don't have a decision based on wind, right? So it doesn't show on this two axis part, right? I need a third dimension, maybe a z dimension sticking out of the slide that would be based on humidity, right? Then I could see that decision boundary, okay? So these are basically axis perpendicular decision boundaries, okay? So the interesting thing about decision trees is when we think about bias and variance, we want to say, well, how expressive is this classifier? Does it have a high bias or a low bias? And it's actually very, very, very expressive because if you go all the way down to a decision tree node, a leaf, you can basically classify on every single attribute. You can say, okay, I'm going to first look at your x1, okay? Decide whether it has a certain value, then look at its x2, then its x3, then its x4, then all the way to xn. Okay, if the attributes for each data instance is distinct, we can always make a decision tree that's going to trivially cut apart the entire data set, right? And basically there'll be one path, one decision path, okay, in this big tree. Let's draw a tree, okay? Okay, except the root is up here, right? Okay, and then there'll be a branch for each of the paths in this. So this is like x1, this is x number 1, okay, meaning first data instance, okay? Maybe I have x number 2, maybe it's like that. And x number 3 is just a branch off of here. It looks pretty similar to x2. Okay, so we can always get J train to be equal to 0 in this case when there's no noise in Y. So this is bad, right? Why is it bad? Because it's too expressive. I don't want it to be expressive enough to overfit. I want it to generalize, right? So basically, we need to find some way of figuring out how to deal with this problem, okay? So one of the ways that we can do it is to make the trees smaller. So we want to lower the variance by cutting the tree off at a particular point. Okay, let's see. Okay, So Chinghan writes that Y is noise free. Yes, so that is one thing that we said here. Let me get that out of the way for a second, right? There's no noise in Y. If there's noise in Y, well, you're dead meat, right? Because then you have two data instances with exactly the same values, and you're screwed. Basically, you always have training error, right? But that's actually typical of a lot of things, right? We've seen in many cases where you either have noisy labels, like or you have noise in your data, right? Like people didn't fill out the or measure properly, and they have different measurements than it should be. Okay, let's see. You said something else, yeah. Um, Curious whether there's a way to tell best JTrain with noisy data. So yes, we want to do that. We can get an idea using almost any algorithm, okay, that it's expressive enough, like decision trees, um, to check whether JTrain is noisy, right? The data set is noisy. So decision trees is the easy way, but basically all you need to do is scan the entire data set, right? And if you see the same data instance twice, but with two different labels, basically you have noise, right? So that's how you can tell, okay? So like we said, what we want to do is to say, take the tree and trim it a little bit. So if I'm gonna draw that tree again, okay, I have this big tree down here, okay, with the root at the top. Okay, this is supposed to be the trunk, right? Our trees are always upside down. We're going to trim it a little bit. I'm gonna give it a haircut, and then leave something like nice and tidy like that. Okay, so that's the idea. You lower the variance because basically you say all those little nuances of the data set that represent the paths past this instance here, you're going to cut it off. Okay, I'm just going to use the decision nodes at this point, and that's it. I only allow you that number of decisions, okay, that number of things before you have to stop analyzing. Just go with your gut, make a decision. Okay, so to do that, we have to decide, we need to know, okay, if you can't make so many tests, which tests are important, okay? So which feature to split on, okay? How do we discretize a continuous feature? And then how do we decide where to stop pruning, okay? Actually, in practice, we actually do the pruning, we grow a complete tree, and like Japanese bonsai, we just cut away things, okay? And then we use the prune tree, okay? So this is the decision tree algorithm. You may have seen it before. This is actually from another book. This is the Foundations of AI book because it's also taught there. Okay, so the basic idea is that we have a set of examples, a number of attributes, and a default. Okay, so the default means what is the decision I should do if nothing else comes out of this. Okay, so usually what we can do is scan the entire data set ahead of time and determine what's the mode of the examples, okay? What's the most prevalent label and use that as a default. So if most of the time I'm going to approve loans, I just say, if you don't have any clue, just give the guy the money, okay? That doesn't sound like a particularly smart bank, but that's the idea, okay? Because this is a recursive algorithm, right? So what we're going to do is actually not do any work, okay, until the whole thing comes clean, okay? So you can think of it like a merge sort or something like this, other recursive algorithms that you might know, okay? So let's step through how this works. Okay, let's see, I want to blow this up, but I'm gonna have to end the show to do that. Okay, so let's throw away our slides here. Okay, so I have a slightly bigger screen so that you can see better. Okay, so all we want to do is take a look at what we're going to decide. So the first thing is, if we have no examples, then that's fine. We're going to return the default, okay? Because I have nothing to recurse on, okay? The second thing is, all of the examples have a clean classification, then return the classification, okay? That happened in the case of Outlook equals overcast, right? So if it's overcast outside, I decided to play tennis regardless of what's happening with the weather, okay? So that's the case when we have a pure node, everything under that particular subproblem is clean. Okay, the other thing we can do is to decide when we don't have anything else to split on, okay, we've already tried all the different things, then we have nothing else to do. It's just not clean. So we have to return the mode of example. So if I have a data set and I have nothing else to decide on, I've already considered all the factors. 5 of the days I decide to play tennis, 2 of them I don't, then I'm going to play tennis. Okay. Okay. Those are the base cases, right? So you know about recursion, you always have a base case. So these are a base case. And then this is our inductive step. Okay, inductive step. So I'm sure you've heard about this from your discrete math or algorithms lecture, okay? So the idea is we're going to postpone the idea of how to choose the best one, okay, to a subroutine called choose attribute. It's going to take all of the attributes in, okay, and the data set and spit back which one is the right one, okay? So in this case, for the example that we looked at just now that's in the notebook, but also in the tutorial, it's going to choose credit history at the top. Okay, once we've done that, we're going to make a new tree, okay? How do we do that? We don't do any work at all. That's the best part, right? This is recursion. You don't do any work until the bottom of the problem, right? So what we're gonna do is for each value, so for example, in the case of looking at credit history, we have unknown, poor, or good, right? Then we're gonna say for each of these values, all right, then what we're going to do is we're going to collect all of the subset. This is the subset of all of the examples that have that particular value. So all the ones with good credit history, for example. And I'm going to do nothing but recurse. Okay, so I'm going to call this algorithm again. Okay, and then after I get the answer, because it's going to return a decision tree. Okay, so it's going to discern a decision tree. I'm just going to add it as a branch. Okay, so that's the whole algorithm, okay? So I haven't done any work yet, right? Basically, I've just said, okay, you do myself a couple times and then we're done, okay? The only thing that we really did is say when we are clean or when we don't have anything else to do, when we get to the bottom of the decision tree, I know what to do, okay? All right. So the next part is on, obviously, then I need to figure out how to ask what's the right feature, right? So the right feature is not that much trickier, okay? So the whole idea is that we want to choose an attribute that has a good way of splitting the data set, okay? It could be all positive or all negative. So you look at this case, this is a case of deciding whether to go to a restaurant, okay? Pretend COVID-19 isn't around, okay? And we basically have, let's see, 12 cases of a past restaurant during history. 6 of them are positive in green, and 6 of them are negative in red, okay? And, we could ask ourselves, were there people sitting in the restaurant or not? Okay, this is a very good criteria in Singapore, right? If you see the restaurant is full, you queue up anyways, even though you have to wait 2 hours for the food. Yeah, I don't know. People do that here. Okay. The other thing you can do is decide based on the type. Okay, like whether it's French cuisine, Italian cuisine, and Thai, or American burgers. Okay, and then decide on that. Okay, and what we could do is decide. Okay, which of these things are good, right? If you look at this diagram carefully, you'll notice there. One of these attributes is much better than the other, okay? So this is the perfect time to see whether you guys are still awake, all right? So I'm going to ask you to use your participants list and indicate for me whether you think patrons is the right one, which would be your yes, or type would be the right one, which would be your no, okay? Okay, everyone is voting for patrons, okay? And that's right, right? The whole point of this is that you get 2 very nice things for free. Like we said before, when we curse, we're going to be able to declare victory for those subproblems, right? Because when there's nobody in the restaurant, don't go there, maybe it's dirty, right? If there's some people in the restaurant, okay, I don't mind waiting a little bit, but I don't want to wait a long time. I'm willing to trust it, I'll go into that restaurant. When it's full, well, I have to think about how hungry I am, right? So if it's really full and I'm not hungry, maybe I need to recurse. I have to decide on something else, right? On the other hand, if I looked at deciding on French, Italian, Thai, or burger, right, I've got a problem, right? What the problem is that even when I look at those subproblems, I actually haven't gained any information. Like when I look at French, it's a 50-50 split. Once I stayed, and once I decided not to go to the restaurant. And same for Thai. Thai, I went 4 times. I was considering, sorry, 4 times. Twice I decided to stay in the restaurant, and twice I decided to leave. Okay, so in this case, I'm not getting any information out of it. Even though I split by type, I haven't made any of the subproblems any clearer to me. Okay, so that's the idea. Okay. So you asked about this. How do we pick a feature and how do we calculate it? Okay. So the idea is we're going to use this notion of entropy, right? So entropy is a simple idea. It's an information theory concept, right? It just says how much bits of data do I need to transmit a message to you, right? So I can think of it, mathematicians use H, physicists use I think S for entropy, it doesn't matter. Okay, this is the same concept, it's the amount of disorder, right? So when you have disorder, basically you're going to look at this case of P log P, okay, as an indication of how pure or unpure that data is, okay? So what we're going to do is go through, okay, all of the classes that you have in our data set. Okay, for example, in credit history, good credit history, bad credit history, and unknown credit history, and see what is the P log P of each part, right? So the idea is that if it is uniform in distribution, okay, the P log P of both of all of the classes will be the same, okay, and it will have a high entropy. When the P log P is unevenly distributed, for example, all of a particular class is indicated, then it will be different, right? So that's how we do it. Okay. So in the case of having only positive and negative features, that's pretty easy. Okay, and you should try to generalize this yourself to the case where you have more than 2 classes. So when we talk about positive and negative here, we are of course talking about our Y values. Okay, so our Y values are, in the case of the bank, approve or reject, right? And in the case of the restaurant, it would be stay and eat, or try another restaurant, go. Okay, so that's what we mean by positive and negative examples. Okay, so we're just calculating that as entropy. So you just need this formula to do that, right? It's just basically the probability, right? So you have basically the probability of that particular example within all of the examples that have that class label. Okay, so on the 2-class entropy curve, it looks a little bit like this. We get the most unsureness when we have 50% of the data indicated as positive and 50% of the data indicated as negative, right? On the other hand, if everything is negative, then there's no entropy at all, right? Because everything is negative. I don't have to transmit any information to you because the default is clear. It's always going to be 0, right? It's the same if all of the things are positive, right? If all of the instances are positive, I just need to agree with you beforehand. You know, if I don't tell you anything, it's positive, okay? So I only describe the negative cases to you in that case, right? Okay, so you can see the entropy curve looks a little bit like that on the diagram, right? We have entropy, sorry, I'm still using squares here. Entropy on um, the y-axis and this ratio here, right, on the x-axis. Okay, so what we can do with entropy is then decide how much of that entropy is due to a particular part of the data set, right? So we're going to say that chosen feature divides the examples, okay, into certain subsets. So if you remember the credit history example or the play sport example, some of them had an outlook of sunny, overcast, or rainy, and we're going to treat each of those subclasses separately, right? So that's what this ratio is for, right? It says, what's the percentage or ratio, not ratio, what's the percentage or proportion of the data set that happens to have this attribute turned to this particular value, okay? And once I know that, I'm going to multiply it times the entropy, right? Entropy is what we calculated on the last slide, right? This H of Sj, okay? So once we have that, then we can calculate what's known as the remainder, okay? How much entropy is left in the problem, okay? Okay, so what we want to do is decide, okay, based on the original entropy of the data set minus what is left after we have split on this data, okay, because we split it right here. Okay, we looked at the entropy of the subsets after splitting into all of these parts, okay? So this was the before, this was the after, right? So I'll just write that down for you. Okay, you can think of this as a diet regimen, right? You had a lot of entropy before. We want to take the diet that's going to minimize the amount of entropy left afterwards. We want a big sum for this information gain. Okay. So we can do that. That's very easy to do in this patrons, and we've done it in the tutorial, and you need to do it for the AdaBoost problem. Okay. So basically, you calculate the information gain of the patrons and the information gain of the type. You can see in the type case, because all of the subclasses are, again, indistinct, meaning they have high entropy, right? Exactly an entropy of 1. We actually didn't gain anything from this, right? This entire sum here is equal to 1. Okay, so 1 minus 1 equals 0. So we get 0 bits of information by cutting on type, where on the case of patrons, we actually improved quite a bit. We gained from an information gain of, an entropy of 1, and we knocked it down quite a bit. So there's only 0.541 bits left, okay? Because basically these two cases have been fixed. Okay, last part we want to do is decide whether to keep the information continuous or discrete, okay? There are algorithms. There's another algorithm that we're not going to teach that's also very easy to understand. It's called CART, okay? Which is another decision tree algorithm, which can deal with continuous features directly. But here we're just going to say that maybe what we want to do is take a continuous feature and discretize it, okay? Cut it into bins, okay? So there are two criteria we can use for that. Okay, one is to decide where to put the split points. Okay, so you can see if I split at C1 or C2, there's actually no difference because, well, it's the same, right? I could choose anywhere between these 2 points, and because my data set only has, at least in training, these points, it won't matter, right? They're all effectively the same. Okay. What we want to do is also decide, for example, to split between examples that have different labels, right? So in C1 and C2, these are good places to put a decision point because the labels switch values there, okay? So we can use these two pieces of information to decide how to discretize a continuous feature after we've decided to pick that particular value, okay? Or in some cases, what we want to do is discretize it even before we pick a value, pick a particular attribute to split on, okay? Okay, so now that we have an idea of how to discretize features, that's fine. Then we can treat them in the usual manner of deciding how to pick features using entropy, because now everything is categorical, right? And so what we can do is decide, okay, when we have grown the full decision tree, how do we decide what to prune and what to not prune, okay? Obviously, we can't prune all the way to the root, otherwise we don't have any decision variables. And if we keep everything to the leaf, maybe it's too detailed, it just specifically fits the data set instead of trying to generalize to the test set. So one way to do it is very simple, and you've already learned it, is to use validation, right? So you can take away a node, okay, and decide to replace it with the mode of the labels, okay? And if that prune tree, okay, works better than the original tree on the validation data set, okay, then you know maybe that's a good idea. Maybe I should have pruned it after all, okay? So it's basically deciding, is this node a keeper or is it not, right? If it didn't help, if it helped you for the training data, which obviously it did because you created that node in the first place, but it didn't generalize to help you in the testing data, which means your validation performance dropped after you threw, when you had it in, and it rose when you threw it away. That means that node was too specific, okay? So it doesn't spark joy, we toss it out. Okay, so that's the idea about decision trees. A very, very simple algorithm, really, really intuitive, and extremely good. Okay, so it's a very effective algorithm. It runs lightning fast. And the best thing about this, which everyone is using it for, is because it's intuitive. A lot of people in their projects or in their other work, in professional work, use a decision tree to do interpretable exploratory data analysis. So that'll be one of the first algorithms they'll use on a data set because it's not expensive to train. And it will tell you a little bit about the types of features you have, okay? Many people need to do it for a decision class, a feature class rather than a particular feature. You can think about, for example, trying to run a decision tree algorithm on a image classification problem where, again, let's say you have 64 by 64 pixels, right? So you have a lot of features, right? 64 times 64 features. And the decision tree is basically picking one pixel at a time. So it's like pixel 74 by 548. What color are you? Okay, based on that color, I'm going to decide, subproblems. Okay, that obviously doesn't work very well. Okay, so you need to have basically a feature class, some type of other thing that's going to abstract away from it. Okay, so if you can think about our nonlinear lecture, when we were saying, okay, maybe you can create from this pixel grid intensity or symmetry, those would be aggregate features that would be useful to feed to a decision tree algorithm. Okay. So the bad is, it's unstable. It's not very stable. It can overfit. Okay, it get everything correct. So it will have very high variance. Depending on which data samples you will get a different tree. Okay, so that's not so good, right? It's very particular about the data set. So we're going to try to solve this on the next part. Okay, there are other problems here that we see. There's no probabilistic way of thinking about classifications. You either get it right or wrong. You can't say something belongs a little bit to this and a little bit of that, okay? And basically, again, because we are doing axis perpendicular decisions, that means we have to have a feature that makes a lot of sense, right? If you don't have features that make a lot of sense, then you have to first create them through nonlinear mapping, or try to learn them, right? Like we saw deep neural networks, it can like create through successive layers some ideas of what types of representations might be good. You could take those representations at the top level and then throw a decision tree at that problem, for example.